And in my previous interaction, what we have talked about is that we can have a symmetrical situation and we can have an asymmetrical situation. And symmetrical situation can be we can talk about the symmetrical geometries in terms of the well-known odd and even functions, and even functions are something like balanced functions. What you do with respect to your right hand, you'll do the same thing with respect to your left hand. The action on the right is same as that of the action on the left. And anti-symmetric means you can rise from one side at the same time you can fall on the other side. What we call as odd functions. So what's going on? What's the intuition here, and what's the audacity of this problem that we have been talking about? And to start with, what we have this famous what we call as infinite potential well. Infinite potential well. And before going into the mathematical formalism of this problem, we would like to have some imaginable tour of this problem. And this problem is ideal in nature. This problem is abstract. This is abstract because what you have is you have infinite one-dimensional potential well. So if it is one-dimensional, I think here I'm missing the line, means I have my particle. This particle is between x equal to 0 to x equal to L, and between this one-dimensional length we have the infinite potential. So the wall that we have here is infinite. Now what does it mean? What does it mean? What am I trying to tell here is that you have a particle, and this particle has to live in a frame which has potential at the edges such that it's impenetrable for the particle. The particle can never ever lose this wall. It cannot cross this wall. It cannot cross this wall of potential. That's what it means. And what we are trying to realize here is how this particle will behave. And at the beginning, what it appears like is, it appears like a prism. It appears like a prism, and the prism for the particle, and what we will see is that this prism will lead to a balanced, harmonious life to this particle, which is allowed to have only certain energies, which will be allowed to have only some forms of symmetric and anti-symmetric probability densities. So what am I trying to tell here is, before going into the demonstration of this formalism, what am I trying to tell is, what you have is, you have the infinite walls, and suppose for the sake of argument, you have a particle. And this particle has to live in this potential, and this potential it's zero. The potential inside this one-dimensional box is zero, that means the particle only has kinetic energy. Now we can correlate this problem to the valley that I have been demonstrating to you. If you remember the valley that I talked about, which has everything as a mirror image. What I'm trying to tell that you have a mountain on one side, you have the same mountain on the other side. You have a stone, you have the same stone. You have a house, you have a house, you have a car, you have a car. Whatever you have in the right, you have the same kind of thing in the left. And you can see, you can look at this potential. If I choose this as origin, you can realize, you can see that there is a perfect symmetry in this potential. And if the particle has to be found, the prism that's there for this particle will allow this particle to have only some specific types of probability densities. So in proceeding from here, so we can understand here, if I choose this as some kind of arbitrary axis, and for the particle, whatever is in the right, it's having the same situation on the left. So certainly this is a problem which is symmetrical in nature. So now, when we will solve this problem, what we will observe? We'll observe that the particle, which is basically manifested as a wave in this case, it will have the probability distribution like this for its ground state. So if you see the probability density for this distribution, you are able to realize that this is purely symmetric in nature. That means the description that you will have here for the probability density will be something like that of a symmetrical situation. That means you certainly will have to do everything with the even function. And then the particle is, see this thing is coming as a result of the boundary. The boundary is dictating, you will see that this boundary is dictating the particle to have the probability density in its ground state in this form. And when the particle goes up, it's given a different kind of probability density. A probability density like this. A probability density which is not symmetric but anti-symmetric. But what we have a particle that's existing over, the probability density of this particle is over these two lobes. And we can see that there's a point where the probability density of the particle is 0 for this first excited state. And you can closely see these two arguments, these two results that we have here. This is purely symmetric. So if it is symmetric, that means it will be a result. You can describe this result in terms of the even function. And this thing is purely anti-symmetric. So you can represent this anti-symmetric in terms of the R functions. So what's going on? What's going on? There's a dictation. The valley that we have here, this infinite potential well is my valley, and this valley is having a pure symmetry in it. And this valley has two mountains, but these mountains have the height of these two mountains goes to infinity. So that means it's impossible for anything to leave the valley. The valley cannot be left. Nobody can escape from this valley. And in this valley, I'm choosing just one particle. So replace, you have to remove all of these, those things in the valley, like a stone, a house, or anything else. There's nothing, there is just one particle and an invisible potential. These potentials at the edges, these are the two mountains, but these mountains are invisible. You cannot see these mountains, and their height is up to the infinity. Now what's happening here? What's happening is you have a symmetrical situation, and in this symmetrical situation, the potential, the walls, the potential at the edges of this one-dimensional box is dictating the particle. And we will see this when we will solve the Schrodinger's wave equation for this problem, where the particle is not acting as a particle, it's acting as a wave. And we will see also from the results of solving the Schrodinger's equation, the results will give us certain quantization rules. So these quantizations that we will obtain, these quantizations are these symmetric and antisymmetric probability densities that we will have. They are basically dictated by this infinite potential. The infinite potential that is dictating the particle that you can live and you can live in a balanced fashion, where you can have harmony, you can have balance, you can have symmetry, and you can have another type of symmetry, what's called as anti-symmetry. And that dictation is coming from choosing these potentials as infinite potentials. So the problem is clear, and we would like to resolve, we'd like to go, and we would like to solve Schrodinger's wave equation for this problem. And we should realize that we have a boundary condition here, moving from x is equal to 0 to x is equal to L. The particle can only have a motion from x from 0 to L. Everything else is impossible for this particle, and we can see that the conditions of wave function, eigenfunction that we have, what we will come up with here is the eigenfunctions, and we will be coming out here as eigenvalues. And these results that we will be obtaining, these results are a consequence of solving the Schrodinger's wave equation in one dimensions, and assuming that the potential faced by this particle is infinite at x is equal to 0 to x is equal to L. At the same time, if we think in terms of the eigenfunction, this eigenfunction will instantaneously be equal to 0 at x is equal to 0, and this eigenfunction will again be equal to 0 at x is equal to L. So this is how the problem will go. This is how we will be using the boundary conditions to resolve the Schrodinger's wave equation for this problem. So before proceeding on, so what's our starting point? The starting point for this problem is the Schrodinger's equation. So if I write down the Schrodinger's equation, so what is that? That is minus I h bar dou by dou t of psi equals minus h cross squared by 2m d2 psi by dx2 plus v of x. Now we can see that the problem that we have been talking about is independent of evolution of time. So if it is independent of the evolution of time, the left-hand side of this equation is immediately equal to 0. So what we are left with is, we are left with minus h bar squared by 2m d2 psi by dx2 plus v of x equals 0. Okay, so this thing is going to be equal to 0, and we can make certain transitions over here. We can see that this what we call as minus h cross squared by 2m, and then we have d2 psi by dx2, okay, plus v of x is equal to 0. It has to be multiplied by psi. Can't help it. We have to multiply this with this will be multiplied with psi. So what we are going to get over here is what we have. This will be equal to 0. Okay, so what is missing out here? I think, yeah, come on. This is the kinetic energy, and this is the potential energy part, and this is the time dependence of the wave function. Okay, so this thing has to be equal to, yeah, this is taken 0, that's fine, and this thing has to be equal to E psi. Right. Sorry. So what we have, because we have to use a Hamiltonian here which does not depend on time. So the total energy of this system, which is the kinetic energy plus potential energy, will be equal to E. And the left hand side of this equation will immediately be equal to 0. So in fact, this term should lead us to the constant, and that constant is the total energy of the particle. This is what it should lead us to. So that's why what I have here is, we have here, instead of 0, the sum of the two energies will lead us to E psi. But one thing is clear, that this E is a constant, and this E is the total energy of the system. And what we can do here is we can re-examine this as minus h bar squared by 2m, then d2 psi by dx2. Okay, what we can do is we can write down this as E minus v of x psi. Okay, fine, because I'm just transferring this v of x on the right hand side. Now what we can do, this 2m will come here, and this h bar square will go down, and minus will come on the other side. Okay, so this thing will be gone. So what you'll be left with is minus. So what we can do is we can transfer that on the other side, and we will have Schrodinger's time-independent wave equation plus 2m by h bar square e minus v of x equals psi equals 0. This is what the Schrodinger's time-independent equation is, and looking for this equation for our problem between x equal to 0 to x equal to L will lead us to this v of x is 0, because the particle has 0 potential between x equal to 0 to x equal to L, and these are the infinite potentials that will not allow this particle to leave this valley, having invisible mountains symmetrical with respect to each other. So what will happen to this equation? We will have a differential equation, d2 psi by dx2 plus 2m by h bar square e and psi equals 0. This is how it will look like, and we can boil down this by a constant. This 2m e by h cross square can be boiled down as a constant, and we can use a kappa, or we call it k dx2 plus k square psi equals 0. Now what we have in front of us is a differential equation, and every differential equation has solution, and you choose a range of solutions for a differential equation, and out of the choice of the solutions, the choice of the solution is basically dictated by the boundary conditions of your problem. So once you choose the solution of the differential equation, then you try to verify that solution by substituting that solution into the original differential equation. So if it satisfies the differential equation, then you choose that equation as the solution of this differential equation. This is how the things are dictated. This is how the mathematical version of solving the differential equations goes on. So you can, for the sake of trying, you can seek for the solutions of this differential equation. But the acceptable solution for this differential equation is if I take this psi as a combination of a cos kx plus b sine kx. Now, whether this solution that we have chosen is a reliable solution, it can be checked. We can check out this solution to be reliable by substituting this eigenfunction in the original differential equation. So once we substitute it in the original differential equation, the overall result should be equal to 0. And we can do that. In a moment. We can do that, and we can resolve that thing. So if this is psi, what I want the double derivative of psi. So what will be the double derivative of psi? So what will be that? d2 psi by dx2. So in first case, you will have the differentiation of cos of kx will give us minus, let me do it in steps. Let's not make a quantum jump. Let's go on like this. So let's go with d psi by dx. What's it that we are going to get out of it is, so a is a constant, and cos of kx will give us k sine of kx, because the differentiation of cos x is minus sine x, and plus b, k will be out, the differentiation of sine x will be cos of kx. So this is our first derivative that we obtain for solving the assumed solution to the differential equation. So now what we'll do is we will again take its derivative. We will again take its derivative and see what happens. So what we will have is we will have d2 psi by dx2 plus, oh it's not plus, this is equal to, okay. So for this, k will be out, sine will give me cos. So it will be a k square cos kx. So minus a k square cos of kx. This will be the first thing. The second thing will be bk square minus sine kx. So minus bk square sine kx. Now this should be the case. Okay, so this is our double derivative of the eigenfunction psi with respect to x. And I would like to use this double derivative in my differential equation that I have. So sorry. So what we can do here is we can have a common here, like we can have minus k square as a common here, and inside I will have a cos kx plus b sine kx. This should be the result. Okay, so I'll be using this in the original differential equation. So this will be the first term of that differential equation. The second term will be k square psi. Okay, the second will be plus k square for psi. And what I have I done it right or wrong? I'm not sure. I have taken this a cos kx, okay, b sine kx, okay. So I have got the same thing. Okay, what I have got? So here I have plus a cos kx plus b sine kx. And we can see this is the positive term and this is the negative term, and we can cancel the two and the result will be 0. That means the solution that we have chosen is a solution for this second order differential equation. So what's the solution? The solution that we have chosen here is psi equals a cos of kx plus b sine of kx. This is the solution, and we would like to make it more accurate by using the boundary conditions in our problem, because psi has physical meaning only when it satisfies some of the important conditions, like the condition of psi must be continuous, the condition like its derivative must be continuous, psi must be single valued, and if we see our problem at the edges of our problem, the eigenfunction will immediately be equal to 0, because there is no chance for the particle to leave that wall, to leave that mountain, because that mountain is infinitely long. So if I think in terms of the boundary, so the boundary I have x is equal to 0 and then x is equal to L. For this boundary, then you have V infinity, again you have V infinity, inside your potential is 0. So So if I look at this point, psi will be 0. So if psi is 0, what I'll get, if psi, at x is equal to 0, psi is 0. So what I'll get, 0 here equals a cos 0 plus b sine 0, because x is taken equal to 0. So we can see here immediately that cos 0 is 1 and sine 0 is 0. That means a is equal to 0. So a will be equal to 0 here. So if a is equal to 0, this part will not contribute to the solution of this differential equation that we have, the Schrodinger's equation that we have. So what will be the solution then? Then its eigenfunction psi, this psi will be b sine k of x. All right. So this should be the plausible solution for my problem. Now I can proceed from here. See, I'm trying to realize the probability density for this particle. I'm trying to realize that where in this one-dimensional box the particle has the maximum probability, the intermediate probability, the zero probability, and what kinds of energies this particle has. So these are my targets, that how the probability density and the energy of the particle is dictated by the infinite walls of the potential, by these two virtual mountains which will never allow this electron to, this particle to leave this one-dimensional box. So immediately from here what we know is, we know that we started with a solution. That solution is the solution of the differential equation. Then we observed that the constant A does not contribute, so that term is gone. Now we have the constant B. We would like to see what this B is, because in order to calculate this B, what is important is that the particle has to be inside the box. The particle cannot be outside the box. So for the particle to be inside the box, its probability density, it must have a normalization constant. It must satisfy the condition of normalization. And as we know, the normalization condition, say if I write it in terms of Cat-Brock, psi and psi should be equal to 1. So this normalization, because the particle has to be inside the box, it cannot be outside the box. For that, I'm using the condition of normalization, which is a very strong tool of the strong tool of quantum mechanics. It falls in the framework of the basic postulates of quantum mechanics. So I will be using normalization condition to calculate the constant B. That will be my target. So what does this bracket tell me? It tells me that the integral that will run from 0, the integral that will run from 0 to L psi star dx must be equal to 1. This is how this Cat-Brock, this bracket will dictate me to calculate the normalization. So this normalization can be calculated by taking an integral from 0 to L, because my particle is confined between these 2 points, from 0 to L. So from here, what we can do is, we can see that the solution that we have a real solution. So if we have a real solution, there is no problem with the star, because the complex conjugate of the real is again a real. So what we will have here, we will have this integral. We will have this integral running from 0 to L, and then you will have this b which you want to calculate, and then you will have sine of kx, and then again you will have b star and sine of kx, and then you will have dx equals 1. Okay, so this b and b star will give us the mod of b square. Let's put it outside the integral. So then you will have 0 to L sine square kx dx equals 1. That should be the case. Yeah. So sine square kx. And all of us know that we can write down this sine square theta as 1 minus cosine, I think 2 theta, divided by 2. We can also obtain this equation, but we'll be using it directly over here. So, sorry. So we will have b squared, and then integral from 0 to L, and then 1 by 2 dx. I'll keep a long bracket outside. I will break it, I'll split it, minus integral 0 to L cosine of 2 kx by 2 and dx. And this thing must be equal to 1. And you can resolve this integral very simply. You can integrate this, and once you will use the limits for this integral, you will immediately get this integral equal to 0. So what you'll be left with is, you'll be left with b squared L by 2. So because the lower limit is 0, the upper limit is L, and once you integrate it, you will get this thing equal to 1. This implies this b squared will be 2 by L, so b is under root of 2 by L. So what we have done, we have used another important boundary condition, and this boundary condition has led us to the calculation of the constant b, and this b has come out to be under root of 2 by L. Now moving on from here, what we will have sine equals under root of 2 by L sine of kx. Okay. Now let's go with another important boundary condition. You have a problem like this. You use the first boundary condition at x equal to 0. Now you will be using the condition at x is equal to L. So you will be using this thing because your potential is infinite. You have infinitely high mountains here. The particle can never penetrate this potential. So at this point, the eigenfunction will be again 0. So at x equal to L, the eigenfunction psi is going to be equal to 0. This is how it looks like. So I can use this condition here. So 0 will be equal to under root of 2 by L, and then sine of kx. Now we immediately understand that this is a value, it's not equal to 0. Then what should be equal to 0 is this sine of kx. So sine of kx is equal to 0. So sine of kx is equal to 0. Now here we can introduce for 0, because what we know is that sine of n pi is equal to 0, where this n is an integral number. It's an integral number. So if it is an integral number, it's a positive integral number. So for any value of n pi, we will have 0. So we can replace this 0 by sine of n pi. So what we are going to do here is sine of kx is sine of n pi, and we can remove the sine and we can write kx equals n pi. Now this x that we have here, it has changed to L the moment I have used the boundary condition. So this x is simply L. So this is KL equals n pi. So we have found the value of this k equals n pi by L. So we can have a generalized eigenfunction here. So we can have a generalized eigenfunction here because the equation has using the boundary conditions has automatically introduced the integral number here. So I will have a subscript for this eigenfunction as psi n equals under root of 2 by L and sine of n pi by Lx. Now this is our eigenfunction, and this eigenfunction will lead us to a set of eigenfunctions, and having those eigenfunctions will lead us to calculate the probability densities, because you simply have to multiply the function with the function itself. That's going to give us the probability density in the framework of Bohm interpretation. So if I choose, now n can have even values, it can have 2, 4, and 6 values, and n can have odd values, 1, 3, 5, 7, and so on and so forth. So you can seek your solution in terms of the even values, and you can seek your solutions in terms of the odd values. If you rightly remember, as I was talking to you in the beginning of this interaction, I was telling you that the particle is allowed to have the probability densities symmetrical in its ground state. So what happens here is we obtain those symmetrical and anti-symmetrical results the way as I had demonstrated you in the beginning. So for n is equal to 1, you may come up something like this. So what's happening here, this is the probability density curve. That means if you are not looking at this system, the probability of this particle to be present in this one-dimensional box has this kind of magnitude, and this is purely symmetrical. We can check it is symmetrical. As I was telling you, if you will draw a bisector here, your right hand will give you the left hand. Whatever you have in the right, you will have the same thing in the left. Maybe this becomes the answer to the question which might arise in our minds when we will calculate the expectation value of momentum. Because the expectation value of the momentum, when we will calculate that will come out to be 0. And that will raise a kind of curiosity in us that if we calculate, when we will calculate the expectation value of kinetic energy, it will have a value. But when we calculate the expectation value of momentum of this particle, that will be 0. So to answer that question, which will come later on, the answer is here. Now, what's going on is, since we can define that expectation to be equal to 0 in terms of the symmetry here. So the particle has the equal probability to be in the left side as that of the equal probability in the right hand side. So the net expectation value of momentum of this particle can be assigned equal to 0. And then another part will come, like as I said, anti-symmetrical in nature. So since they are both beautiful, this is not asymmetry, this is anti-symmetry. I mean, this is also symmetry, this is symmetry, this is also symmetry. The only difference is this is positive in all cases. It has everything happening in the opposite direction. The things are happening exactly in opposite direction, but both are symmetries. Both are the symmetrical results, and these results has a resemblance with that of the violin. The violin can choose only certain tones that you can then modify by superposing them onto each other. But here you have the beauty, you have the symphony, you have the balance, you have the symmetry, and this symmetry is dictated by these potentials, by these two mountains which have told this particle, come on, you cannot leave this prison, but you can have harmony, you can have balance, you can have symmetry, you can have anti-symmetry. This is how the imaginal world runs, which may not be real, which is not real, but we start with that imagination to take us to the real situations. So where we have been till now is we have got this eigenfunction. So we have got this eigenfunction, and we can calculate the expectation value. Say, for example, we can calculate the expectation value of momentum here. So expectation value of momentum. Okay. So what is expectation value? What's the operator P? That is minus IH bar dou by dou x. Now, if you want to calculate the expectation value, it will be psi P and psi. This is how we can calculate the expectation value of momentum. And we can write that down this in integral form. So this is integral